Okay. I think everybody submit the video, right? First video project, right? Yeah, that's the first time, and we will have several more in the semester. So just I think the first one always, a little bit difficult, and you don't never experienced this before. Even submission sometimes have difficulties. Now I think you are after the first one, you should be expert on YouTube at least. Okay. Okay, let me share my screen. Let's continue on chapter 3. Last time we did the surface force, right? We did the surface force, and I chose a relative difficult example for the surface force problem. Okay, this is the one, right? So hopefully you fully understand this problem. I think that will be really helpful for you to understand the concept here, right? Two things here. To calculate the force on a plane surface. Okay, so I guess for now you should remember how to do that, right? Just the area times the average pressure on the surface. Okay, the average pressure will be the pressure on the centroid location, right? We did a quiz last time. I kind of force you to draw this with putting a mark on the centroid, with putting a something like this. Okay, so just keep in mind, in this type of problem, you need to understand a little bit of the geometry. Okay, so for a shape, you need to know where the centroid is in terms of the coordinates, right? Then you need to know how to measure the depths, water depths on top of the centroid. Okay, sometimes just like this problem, you need to use a little bit of geometry, right? Then that's it. Gamma times the water depth on the centroid, that's the average pressure, okay? Then times area. Then you need to know the combined force, the location, where the force applied to, which is called the center of pressure, CP, right? So that equation to calculate the YCP, which is from the distance from that CP point to the surface of the water, which is sometimes it's not the one you directly needed for solving a problem. You have to convert, okay? That's YCP. YCP is not from the starting point of the plate to the center of pressure. No, it's not like that. It's from the center of pressure to the water surface, okay, far away. So I think we figured then we can use YCP minus Y bar as a better form, okay? So the YCP equation equals to something plus Y bar. So YCP minus Y bar equals to something that would be easy to memorize. The YCP minus Y bar is the distance between the center of pressure and the centroid, okay? So actually that equation tells you the distance between the 2 points, which is more often used in solving problem, okay? YCP minus Y bar. So you can exclude the distance, between water surface to the plate, okay? So I guess that's the key for solving plane force problem, okay? Okay, we did the example. So I assigned the homework problems on Moodle. I really like you to practice some of the problem at least, okay, for plane surface. So let's have a quiz on next Tuesday, not today, a quiz on next Tuesday, just on the topic of plane surface. How about that? Although I assigned a lot of homework problem for chapter 3, cover everything. Let's focus on the quiz on the plane surface, okay? Just prepare a little bit. It won't be exactly the same problem as the homework problem, but it will be close, okay? It will be close to one of the homework problem maybe, okay? So today, let's look at the curved surface. Let's continue on the notes. Curved surface, okay? So let's do an example. And curved surface will be the way we calculate the curved surface will be used to derive the buoyancy force. Okay, the buoyancy force basically is the difference between the force applied on the bottom half of the object and the top half of the object. Think about that object is in the water. If you separate the object into top half and the bottom half, each half will experience a hydrostatic force from water. Okay, think about it. The lower half is lower, right? Even without detailed calculation, what the force is, you know, on the lower half, the hydrostatic force will be higher. It will be greater than the top half. Do you agree? Top half is shallower, okay? Lower half is deeper, okay? So that's the key. That's the reason that the buoyancy, okay, this is a totally different explanation comparing to what you learn in physics. I know what physics teachers teach. They call it replacement, right? The object replaced by the water, same volume. Then if the object is heavier than water, the object will sink. If the object is lighter than water, it will float. That's why you have buoyancy force. But that's not the reason. That's the observation, right? Okay, actually the reason is what I just said. The bottom half of the surface experience a higher hydrostatic force than the top half of the surface of that object. Okay, so the difference is the buoyancy. Okay, let's come back to the curved surface. Let's see a very simple curved surface. Okay, let's say you have a curved surface underwater. Okay, from what we learned in the previous class on the plane surface, we know actually we need to do integration, surface integration to kind of find the overall force. It's a distributed pressure, distributed force, everywhere different, right? You have to do force times area, force times dA, then take integration, then to calculate the overall force. That's the standard procedure, okay? It turned out to be in the plane surface, we actually derived it. It's turned out to be a lot of terms canceled, a lot of things canceled out, and it turned out to be actually a relatively easy form, okay? You don't really need the integration, okay, for plane surface. But curved surface, probably if you want to go straight, you know, go directly use the integration, you cannot cancel anything. You're gonna keep the integration sign there. So in other words, you probably need to do integration to directly calculate the total overall distributed force on the surface. Okay, so that's the standard procedure. But still, we don't like to do integration. Okay, we don't like to do the integration. So let's see, what can we do? Engineers are smart, right? So let's see what we can do to avoid taking integration. Don't get me wrong, I'm with you, okay? I'm an engineer, I'm not a mathematician or physicist. I hate integration. I'm with you, don't worry about it, okay? We're just trying to do something, you know, make everyday field engineer life easier, okay? So if we can avoid integration, I can, we will do that, right? If I have to, then I have to. So what is the hydrostatic? Let's say, I think some of the students confused, hey, both sides have hydrostatic force for it, right? So we don't want to look at the both sides. If you look at the both sides, then become, you know, the difference become buoyancy, okay? Let's say in one side of the surface, okay? One side of the surface. Let's say this thickness of the surface is infinitely small. So the both sides have the same force applied to it, okay? So let's say in one side, I'm holding it, okay? The other side, you have hydrostatic force, it's balanced, let's say. So in order to calculate force, I need to hold it, I need to calculate the hydrostatic force, right? FH, let's say hydrostatic force. Okay, so we don't want to directly do this. You have to do integration, pressure times dA, you know, everything. So let's make it a smart move. okay? Let's separate it into two components, just like you deal with the force and the vector, right? You separate it into XY component. Let's say, hey, this force, can we create a vertical and a horizontal virtual surfaces? Okay, if we can find out the force on the plane surface, this horizontal virtual surfaces, then maybe the overall force is related to that two components. Maybe not exactly the same, but they are related. Okay, maybe we have a hope to do it easier without using integration, because in the plane surface, you don't need to do integration, right? Okay, that's the logic. So let's cut into these two planes, vertical and the horizontal plane. Let's say I have a force F1, F2. These two plane surface that experienced, okay? So my logic here is I need to find out what F1 and what F2. Then what is the relation between FH to F1 and F2? Okay, so that's my plane. Okay. Okay, so let's say what is F1? So this is F1. Okay, so my supporting force here, I can separate into two components. Okay, try to match the F1, F2, the horizontal and the vertical force. Okay, but notice my supporting force is basically exactly the same as the hydrostatic force, the plane with surface we experience. So it's action reaction, right? I just want to make the direction here to make it more clear, you know, to explain. Okay, clear for you to see it. Okay, so this is basically the hydrostatic force. Okay, so let's say Fx and Fy. Okay, so what is the relation between F1 and Fx? Fx is the x component of hydrostatic force. Fy is the y component of the hydrostatic force. Okay. Anybody from looking at this? F1 and Fx, is there any, are they related?
Are they equal?
Are they equal? Let me ask the rest of the class, are they equal? They're totally equal, right? Think about an example, just like I have a table here, okay? Hey, Arthur, you standing next to the table, one side of the table, your body lean on the table, okay? So I'm on the other side of the table, I'm pushing that table. I apply 100-pound force to pushing that table. What do you feel? You will feel the table pushing you. Okay, seems like my force is totally transmitted through the table to you. Okay, so it's the same. Okay, so this horizontal force F1 equals Fx. Great. So we find a relationship here. So if we can find out the F1, then I should be able to find out my x component of my hydrostatic force. Okay, good. They're equal. Okay, so what is F1? Anybody? Do you know how to find out F1? Now, this is the knowledge we did previous couple classes, right? For a plane surface. Okay, depend on the shape. Okay, you should be able to find, now it's plane surface, nothing new, nothing curved. F1 is just the force on this plane, vertical plane. Okay, so find the centroid of that surface. Okay, measure the distance between the centroid to the water surface, top water surface. Gamma times this h, that's your overall force on that vertical plane surface. It's a virtual surface, but it's plane. Okay. So F1 you should be able to calculate. So you know the x component of your hydrostatic force. Hey, that's great. I don't need to do integration here. I'm still doing the plane surfaces. Okay. I'm still doing the plane surfaces. Does that make sense? Everybody follow me? Okay. Now let's look at the F2 and the Fy. Okay, F2 and Fy. Oh, are they also related?
Yeah, it'd be F2 would equal Fy plus the weight of the.
Exactly, they are not equal anymore. So then this chunk of fluid also sitting on top of the surface, it gives a weight, right? It has a weight. So F2 is the force on the plane surface, horizontal plane, right? Virtual plane, plus the W. Hold on, let me rewrite it.
So is it weight of the water or weight of the surface?
Weight of the water. Look at my drawing, free body diagram. Okay, look at the arrow. Arrow is F2 is going down, right? Is that right? And the water give a weight also going down. Okay, your Fy is the supporting force going opposite direction. F2 plus W equals Fy. Is that right? Everybody? Okay. So still, although it's not directly equal, still there's a relation here without integration. No integration, okay? So can you find out F2? Can you find out W? I think you can, right? How do you find out F2? It's a horizontal plane. What is the F force on a horizontal plane? Come on, force on the horizontal plane. Before you take this class, you should have even know, right? It's just pressure times area. The pressure is the same, horizontal. Gamma times h, right? Horizontal plane, you don't even need this chapter 3, to know how to do it, right? Just P times A, okay? That's a piece of cake, good. Can you find out W? Well, W is problem dependent, right? It's need the gamma rho G times the volume, right? Gamma times the volume is weight, okay? So if you can find out the weight, find out the volume. So need a little geometry. You need to find out the volume of this thing, okay? Volume times gamma is W. Remember, I want you to remember some of the equation, okay? Gamma times volume, okay? In reality, so if a surface like this, you can even measure the volume. If it's a bowl, for example, if it's a bowl shape, you can actually measure the volume, fill it with water, see what the volume of water is, right? So you can find some way, some independent ways to find the volume of this chunk of fluid. Okay, then you find your Fy. So if you have Fx, Fy, you can have a combined force calculated. Square root of Fx square plus Fy square, right? That's what the combined force is. Okay, is that right? That's the equation. You should remember those things. Right? These are the basic. Don't forget. Okay, if you memorize as an engineer, the difference between engineer and regular people is you do memorize something. You can talk engineering. You use the engineering way. Okay, so don't think I don't have to memorize. It's everything in the book, and I can. But when you talk to people, sometimes they can tell if you're good or not, right? So, right, this is the fundamental, very general surface, arbitrary surface underwater, okay? So it's a curved surface. We totally don't need the integration, basically, okay? We cut into two planes, vertical plane and horizontal plane. That's it, okay? Separately find out the force on the vertical plane and horizontal plane. Then find out the weight of the fluid within these two planes, okay? So that's the procedures. It could be tedious still, but still there's a way to do it. You don't have to do integration. Okay, so let's go further down. Let's say, hey, we have two half of this surface. Make it a bow. Okay, make it a bow. Okay, so what is the hydrostatic force? Again, I'm drawing the reaction. Hydrostatic force supposed to be applied on top of it, right? Let's draw the reaction here. FH, hydrostatic force. Okay, what are the equals? Okay, again, I think this is easier than the previous more general case. You just need to create one surface on the top, because the other surface, hey, actually vertical surface outside is like this. Okay, your force, you have two half of this. Okay, so both F1 here, let's say F1 point, they're canceled. Okay, they have exactly the same area and they are vertical. Okay, so the horizontal force on this case is gone. Okay, easy. So you only have the vertical force, let's say F2. Okay, then plus, again, now you need to plus the W, the weight under that virtual force. Okay, is that right? So this is the easier. Okay, this is like a more special case, right? So the hydrostatic force equals to F2 plus W again. Okay, there's no horizontal one. That's it. The hydrostatic force is just the Y component. Okay, so can you calculate? Okay, let's write it down. Say, hey, if you can calculate this, what is F2? Okay, give me an expression. Pressure times area, right? Is that pressure times area? Okay, so let's put area as A. Okay, pressure, gamma times H times A, right? Let's say this is the height is H underwater. Okay. So it turned out to be, hey, you see, let me draw this cross-section surface. I'm talking about the A, right? It's a bow, so it's a circle, right? Whatever shape, it doesn't have to be circle. Okay, so it's just a surface. Okay, A times H, what does that mean? Again, here is gamma times the volume inside. Okay, the weight is gamma times the volume inside the bow. Okay, V is volume. Bow, how about that? BOWL, gamma volume of the bow volume. Okay, so hey, look at this. What is H times A? Are you curious? So initially, because we do gamma times H, right? It's pressure times area. Now we can separately look at it. The gamma times what? H is what? H times A is what? A is the area of this. H is the height of this, right? It seems like that's a cylinder. Volume of that cylinder sitting on top of the bow. Okay. Let's say cylinder plus gamma times V bow. Okay, it's getting better. The equation become more easier to understand. Can we group the gammas? The two terms, right? Gamma times what? Volume of cylinder plus volume of the bow. Okay. Equals what? Let me put the volume total here. Total. What means total? Look at this. This is just the total volume sitting on top of, exactly projected on top of the bow. Total volume. Okay. Total water volume. Does that make sense? Equals what? Gamma water times the total volume basically is the weight, total, let's say, bigger capital weight of water sitting on top of the bow. But it's on the projected area of the bow. Okay. Okay. So we'll come back to derive the lead back to a very, very common sense concept.
So the cylinder stops at the top of the bowl. I see you have the, your drawing goes down below it. Is that not supposed to count towards the water for the volume of the cylinder?
The cylinder is from, so the entire volume we're divided into two portions. One portion is below the horizontal surface inside the bow. I call it the volume of the bow. Okay. One portion is start from the horizontal surface to the water surface. That's the cylinder. Okay. So that's the volume of cylinder. So I just want to see at the end, you will see the total volume here. It's the volume of the cylinder plus the volume of the bow. What does that mean? It seems like a total projected volume on the total volume of water on the bow surface. Okay, but not everywhere, just on exactly on top, vertically on top of the bow surface. Does that make sense? Everybody, is that clear? Okay, so the reason I go through this is we start with a very like a complicated engineering concept, but eventually lead back to a very, very common sense idea. The force on the surface of this bow is just basically the total weight of water sitting on top of it. Everybody? That makes sense? Okay. Kind of like we proved it, proved our complicated hydrostatic principle is correct because this is common sense at the end. It is true. Okay. So, okay. Any questions so far? Okay. Let me save my paper by extending this case into two surfaces, top and bottom, and enclosure. You know, I'm leading to the buoyancy, okay? The enclosure, okay? Enclosure. So you have two surfaces that's divided into two halves. One is bottom half. Let's say, let's put the opposite direction as the hydrostatic force. It's a reaction force. No, actually, it is actually the hydrostatic force. It's exposed to the outside of the water. So water apply the force to the surface like this. And for the top surface, you have a water force going downward. F bottom, let's say. F top. Okay, the top surface going downward. The bottom surface going upward. Okay. Now, let me ask you this, which one is bigger? I already said it in the beginning, right? Bottom force is bigger or top force is bigger? Because the bottom half is lower always. if it's lower, the pressure is bigger, the force is bigger, is greater. Okay, so the top half, the force F top is a little bit smaller than the bottom half. Okay, they are the difference in forces between top and bottom. They drive the body upward. Okay, so let's look at, I already know from the previous example to show you what F bottom is just totally this thing. Okay, gamma times the total volume sitting on top of it. Okay, but how about F top? From the same logic here, I know it will be gamma times the total volume on top of it. How about that? Okay, let me draw it here. A cylinder, okay? Exclude the inside area. Okay, so this is the volume I'm talking about. The volume on top of the top surface. Let's say this is called V top. Volume top. Okay, so F bottom the same, doesn't matter what kind of situation, the shape the same, location the same. It should be exactly same as the previous derivation. So it will be the total volume sitting on top of this bottom surface, which include the top volume as well as the volume of entire bowl inside. Okay, so F bottom is total means gamma times the volume of top plus the total volume of the enclosure. That makes sense? Okay, for the bottom surface, it doesn't matter they're the top half or not. As long as you're inside the water that deep, you will have that same force, okay, from the water to you. Okay, do you agree? That will be the same as only half, as long as the shape is the same deep. Water don't know, it just apply force to that surface, okay? You don't know, it doesn't know whether you have top half or not. So it's the same. So you need to consider the entire volume sit on top of the bottom surface, which is the volume on top here, which is shaded volume, plus the entire volume of the body. Okay, so the difference, F bottom minus F top will be what? Gamma times V top plus V minus V top. Okay, right? That V top is canceled. Okay, it become gamma times volume, which is the volume of the object. Okay, I put OBJ here. Object. Okay, so we derived, okay, that's the difference between bottom half and top half. That's always you have a upward force, we call it buoyancy force, FB. Okay, if it's a submerged object, you always will experience a upward force, which call buoyancy force. No matter how heavy, I don't care how heavy this thing, as long as it has a volume, okay, it will have a buoyancy force, which is always upward. Okay, because always if there's a body, there's a volume, then there's always a bottom surface and always a top surface. Bottom surface will always have higher force than top surface. It always will give you a buoyancy force going upward. Okay, that's the true mechanism of buoyancy. Okay, I don't think in the high school physics we taught like this. Okay, but that's the real reason. Okay, everything is from force. Engineer, we deal with force, right? Everything is force. Eventually, it's the force that causes all the changes. Okay. So now we derive the equation for buoyancy. I don't think the yeah, I don't think this buoyancy principle, the equation is too difficult. It's very simple. Okay, but sometimes you need to be careful. Okay, on one thing here, for calculate the buoyancy force itself. Okay, I don't care the weight. It could be heavier. The weight for the object could be more than the buoyancy force. Then the object will sink. But it doesn't mean if it's object sink, it doesn't mean that no buoyancy force. So buoyancy force is still there. It's just because the weight is too much. Then the thing is still, the body is still sink. Okay, but if sometimes the body of the weight of the body of the object is light, then the buoyancy force is greater than the weight. Then the body will go up, will go to the surface, will float. Okay, is that right? Okay, don't confuse the buoyancy force with whatever eventually happened to the object. Okay, that's a common mistake students have. Okay, the thing is actually sink on the bottom. What do you mean that the buoyancy? It still has buoyancy there. It's just because the weight is too much. Okay, okay. So remember this. This is one more equation you need to remember. Gamma of water. Okay, be careful. I need to write here. It is gamma of the fluid. Be careful. Because when you calculate the weight of the object, it's also gamma times volume. Remember, I just mentioned I want you to memorize. But when you calculate the weight, it is gamma of this object times the volume. Okay? When you calculate the buoyancy force, it's gamma of the fluid times the volume. Okay? There are subtle differences here. Okay? Can you make it right? Okay. So that's important. Okay, you have an object there. Okay, you always have a W of the weight of yourself. You always will have the buoyancy. So it's a competition between weight and the buoyancy force. It's a competition in each case. Is it greater or less or equal? Okay. So there will be three outcomes. If W is greater, it will sink. Is FB is greater, it will flow. What if they are equal? If they're equal, they just stay there. Okay, stay submerged. The force is balanced. Okay, so let's look at the example. A very simple one first. Any questions before I move on to the example? Okay, I like you
I
to.
have a question.
Yeah, go ahead.
If they're equal, wouldn't it be the object be half in the water and half out of the water?
Okay. If it's equal, it will just stay there, whatever the initial position is. Okay, it just don't move because they are equal. Okay, it just stay there. Okay, so if you place it somewhere, it just stay there. Okay, so let me ask. Yeah, you reminded me. Okay, I have a good question here. You remind me. Now let's say, hey, the FB is greater than W. Okay, so if it's greater, it's not balanced, right? You have an overall force, right? Yeah, okay. What happened to it? It goes up, right? It go up. When does it stop? Oh, well, first of all, will it stop? Will it keep going like a shoot into the sky, like a rocket? So when does it stop, and why does it stop? What happens? Then something must happen, right? It stops. Where does it stop? It go up, right? If buoyancy force is greater, the weight is light. Okay, you push a wood object into the water, then you let it go. It go up. Okay, wood is lighter. Okay, so when does it stop?
As soon as the object is out of the floating completely on top of the water.
Okay, it stopped in here. So why does it stop? What happened? See, you have forces. Forces not balanced. Why it stops?
When the weight of the object that's in the water equals the buoyancy force,
Okay, so what happens? The buoyancy force become equal. It's greater than W, right? Why it suddenly equals? Why it decreased?
there's decreasing gamma when it comes out of the water.
No, it's not decreasing gamma. It's close. There are two terms for buoyancy force.
In
Decrease in the volume that's submerged.
That's right. It is this. Then this thing is getting smaller, decreased. When it goes to the surface, see, look at this drawing I did here. Is the submerged volume decreased? That's the reason it stops there. The buoyancy force gets less after you reach to the surface. So in that sense, based on the information, based on the property, you can actually predict, actually calculate how much the object will be above water, right? You can actually calculate how much of the volume is submerged, okay? When they have the different properties, different gamma between the body and the water, okay? So again, see, look at this equation. The difference delta between the buoyancy force and the W is gamma of the object times volume minus gamma of water times the volume, same volume, right? So it is volume times gamma of object minus gamma of water. That's what high school physics teacher says. Displacement, right? You try to compare rho g here, right? Which rho is heavier? Okay, if it's heavier than water, then it sinks. It's lighter than water, then go up. Okay, the volume displaced by the water by this object. Okay, it dictates it goes up and go down. Okay, okay, so that's the principle. Let's look at the example. So let me ask you why it goes to the bottom. If the weight is greater, it goes to the bottom. Why stop at the bottom? Right?
They have nowhere else to go.
This is not the explanation from the engineer, okay? The engineer should say, because the bottom supply a supporting force to it. The normal supporting force on the bottom. You reach the bottom, the bottom have the supporting force to it. Then make it balance. So you can actually calculate the supporting force from the bottom. That's the difference between the buoyancy and the weight, okay? Okay, so it's always force. Everything, you know, is related to eventually end up in the force characteristics, okay? Force that dictates the motion and what will happen, okay? Now let's look at an example. Let's see, you have a sphere underwater, okay, connected to the ground, the sea, this is seawater. Okay, so that's like a balloon, right? 1.5 meter in diameter under, let's say, Pacific Ocean. Okay, we do have a lot of stuff like this under those Pacific Oceans, right? You know, it started from the Cold War. World War II, they start to put down stuff, surveillance for spy purposes. Okay, we still have a lot of that down there. Let's say this weight of the object is, the W of this object is 8.5 kilonewton. I know the weight of this object, okay. I need to know how to design the support. Do I need a solid support, or do I just need a cable? Okay. So that's the problem. Okay, so indeed, if you want to design something like this, hey, you are the engineer, let's put you in the shows. Okay, you design, I have a balloon, I have a surveillance stuff, instruments in there. I weighted 8.5 kilonewton.
I thought you didn't like kilonewtons.
But for the problem statement, I'm okay with it. I'm saying in the calculation, when you write down the number in the calculation, I don't like kilonewton. I like the newton. Okay, but they give you problem statement. That's whatever they want to give you. Okay, I cannot control. But when you convert it into your calculation, okay, convert it into your calculation procedure. Write down the numbers. Put down 8500. Okay. Okay, so that's a design project to you. Okay, so you are engineer. Okay, I know this thing. I weighted, put on land is 8.5 kilonewton. Okay, now I need to put it under the Pacifics. Okay, so what should I design? Is this a cable down there, or I should put a solid support down there? Basically, the question here is actually ask, is it tension or compression in this support? Okay, based on its tension and based on is a compression, then there will be different designs, right? Either cable or a solid support. Okay. That makes sense? You know, if it's compression, you have to have a solid support, right? If it's the tension in there, then you will probably need a cable to, you know, stop it from flowing away. Okay. If it's a solid support, that means the thing too heavy. You're gonna sink into the ground. You have to support it. Okay. The cable cannot support the body from going downward, right? So that's the question. So what is it in the structure here? Is it tension or compression, and how much is it? Okay, so these are the questions. Okay, so do you know how to do it? This is simple.
Wouldn't we need more information than you've given us?
That's it. That's
Like
all you need. That's all you need.
I mean, if the buoyancy force.
So don't think too deep before you draw the free body diagram. You think too much, you're not gonna get an answer without seeing your force structures, force balances. Okay. Okay. That's my suggestion, recommendation to you. Okay. You become a real engineer is what you see a problem. It will be safe for you to draw it, to put on all the forces. Then let's talk about it. Okay. So let's draw it. Okay. Do you know how to draw the free body diagram here? That's always what I emphasize on the statics topic. Always free body diagram. Okay. So how many objects in this case? You have to identify an object first, right? For drawing free body diagram, there must be a body here. Okay. Which body is you want to start with?
There's two objects, but you don't have to draw the support because it's a two-force member.
Okay, I think that makes sense. That's a point. So you decide to draw this blue or whatever spherical object. Okay, let's draw it. Maybe that can answer your question. You had a question, right? So let's draw it to see if we have enough information. Okay, well, it's easy to draw, right? Draw that circle. Nobody don't know how to draw that circle, right? But keep in mind, after you detach this object from the support, what you need to do? Before you put on any original force, you know, okay? As long as you detach or you draw the object with the support, okay, then you need to replace by a force. If you detach this object from the support, you always need to replace by the supporting force. Okay, that's a rule of thumb. Remember, that's the key for everybody. I don't know the direction of that supporting force in there. I don't know. Okay, doesn't matter. If you don't know, put an arbitrary direction. You want to put upward or downward. Doesn't matter. If you put the upward direction, any direction, if the calculation turns to be negative, that means your direction is opposite. Okay, it turns to be a positive value, that means your direction is exactly correct. Okay, so from my experience, I want to spend less time thinking about those things. Okay, I always put a unknown direction force. I put it in the positive direction. I don't know the direction. Then how about just put it upward? Let's say I put a number T, put the letter T. I just assume it's a supporting force, right? How about that? Because I don't know. Eventually, if T turns out to be negative, that means it's supposed to be the opposite direction. Okay? So just arbitrarily select the positive direction if you don't know the direction, okay? It's kind of safe. Okay, everybody follow me? Okay, good. So don't even need to spend much time, just put it on the supporting force here. Okay, then the initial forces, what do you know? What do you have? I think I have the weight
and buoyancy.
Weight and the buoyancy, FB. Okay, I guess that's it. Everybody agree? That's it, right? Simple. Now you can immediately write down the force balance. Let's see, then let you see. I know the T is my unknown, right? If I know everything else, hold on. Okay, T is my unknown. So this is my equation: FB plus T equal W. Everybody agree? Can everybody write on this? I think so, to this point, you should be able to write on this based on looking at the free body diagram, right? Okay, so it's good. I like it because my unknown, it is in the equation. That's good. Okay, so your goal is just to find out W and FB. That's it. It's all the problem. It's extremely simple. Okay, do you know W? That's given. Not to put 8.5 there. 8,500 Newton there. Yeah, you see the answer will be wrong if you put 8.5 in there. Okay. Okay, good. I can just add in there here. 8500 Newton. Okay. So only thing here is just to find out the FB. Okay, what is the equation for FB?
Gamma
of the liquid times the volume of the object.
Okay, let's say seawater, volume of the object. Obviously, there's only one volume here, right? One volume here. So, okay. Now I'll come back to your question. Do I have everything else, Josh, to solve this?
Yeah, the gammas for seawater will cancel.
What do you mean it will cancel?
Weight is the gamma of the fluid times the volume inside.
No, gamma is, first of all, volume, weight is not the gamma of the fluid. Volume, the weight is just the gamma of the object times the volume. Okay, it's a material density, material specific weight, right? But actually we don't need, it's given. We don't need that equation to solve the weight. Weight is given, right? As a number, it's already given. Okay, so the gamma of the seawater is not canceled. You're right, actually, we need to know information of the gamma of the seawater. Okay, seawater is a little bit heavier, but it's a property. Still, you can get it.
1.03 is what the book said.
Yeah, it's specific gravity 1.03, let's say. Okay.
All right, yeah, that's what I was looking for.
Yeah, you're right, actually. We do need the density of the seawater.
So without that, I wrote that if the buoyancy force is greater than water, then we need a tension force going down. If the buoyancy force is less than water, we need The
You're
tension
right.
force
You're right.
will go.
Exactly. So you actually think the physics, for this the same situation, you actually have a good conclusion. Here, I'm not even thinking about that physics. I wanted the t to tell me if the t is negative or positive. I like the math to tell me. Eventually, my solution, my answer, let it tell me it will be tension or compression. Okay, that's one layer of verification. Okay, so let's do a calculation here, can we? So gamma of seawater is 1.03. I'm giving specific gravity, right? Times 9810 Newton per cubic meter. Does everybody understand this? I think this is we use the many times, right? So volume of sphere. Do you have an equation for volume of sphere?
4/3 pi times the radius
How about
cubed.
how about diameter? Can we use diameter? It's given diameter.
Oh yeah.
So 1/6 of the pi diameter cube. Okay, that's the same thing. Plus t equals 8,500 Newton. This is obviously cubic meter, right? Okay, so based on this calculation, let me see my value. So my t is negative 9350. Okay, based on this calculation, it turned out to be t is the negative value, negative 9,350. Is it tension or compression? Negative means my initial specification of t going upward is wrong. The t is downward. Okay, so the t is downward, then it is a tension. Okay, it is not a compression. It's a tension, then it has to be cables there instead of the solid support. Okay, so that's what the design. Josh, you're totally right. You said it's if the density is heavier or lighter, right? If you're comparing to bit, but it has to be comparing to the density of the object. I don't know. We don't know the density of object. It directly give me the weight. Okay, so you can back calculate based on the weight, you can back calculate the density of the object. Okay.
Yeah,
so,
I just made that observation looking at the free body diagram
yes.
on which way to put it.
Yeah, which one is exactly bigger? Okay. Okay, see, this is a simple example, okay, using the buoyancy principle here. Okay, the thing I want to emphasize here is for those unknown direction forces on free body diagram, don't be afraid. Don't be afraid. Oh, there's that force. I don't know the direction. How do I draw it? Okay, I'm very comfortable with putting arbitrary direction if I don't know the force direction. Okay, I'm very comfortable with that. I like things I don't know. I just put arbitrary direction. Then let the calculation eventually tell me the direction of that force. If it's negative, that means it's opposite to what I set it up. Okay, if it's positive, that means the direction I put on the free body diagram is correct. Okay. Is that good? Any question to this problem? Everybody clear? 100%? Good. Okay, I have 15 minutes. Let me give you one more simple examples. Okay. It's called hydrometer. Okay, very simple design to measure the density of an unknown fluid. Okay, to measure density of unknown fluid. Okay, this is usually I like to even make it into a design project. So you guys can actually design, hey, I have a tube. Let's say I have a tube. Okay, I have a marker. I draw a marker, but it doesn't look like a rocket. Okay, let's say I have a marker. I have a tube. Okay, I give you an unknown fluid. Okay, so hey, you're an engineer, right? How about you design for me? Okay, obviously you're gonna use the buoyancy principle here we just talked about. Okay, so what's the strategy? Because it's a super simple problem. If I just give you the problem statement to after you ask you to do it, it will be too easy. But let's do a design project. Let's say, hey, to see if you have the thought of doing some design, you know, you're gonna utilize this buoyancy principle, right? Let me give you a hint. Let me give you a little weight. Make this empty tube a little bit heavier. Okay, I give you a little bit of weight. It will be a little bit heavier. Okay. So what is the thought process? Your thought process should be start from the equation. When you look at the equation, then let it tell you what to design. Okay. That's a process for engineer. Instead of, this is the engineering design, instead of the, like a lot of people do the, like what, garage engineering, you know? I do that. I play with stuff in my garage, right? Without the pen and paper even, I just do whatever I want to do. Okay, but the real manufacturing engineering process should be different. You have to be strict, have to make sure, guarantee, you know, safety and the productive. Okay. So what you do is you are looking at the equation. Let the equation tell you what to do. Okay. So equation tell you. So my equation, what we're gonna do definitely will be this. Is that right? I think I have an unknown fluid. I have some device. I want to place that device into the fluid. Eventually, it will be balanced. It will be floating, I think. Okay. If it's not floating, probably difficult to do. If too many unknowns. If it's not floating, then you have another variables in the equation. It will be 3 variables. They will be difficult. For example, it sink to the ground. Then you have a supporting force in the equation. I want less the better, because there's less unknowns in there. Okay. When I design it, it will be a little bit easier. Okay, so I probably try to make this thing float in there. Okay, so the equation will be, if it floats, it's just balanced. Okay, buoyancy force equals to weight. Okay, you still have no clue how to design, right? Let's expand the equation. Let it tell you what do you need. Then you go find it. Do the design to find it, right?
Can you describe what you drew before we go on?
I didn't do anything yet. I didn't do anything yet.
Okay.
I just said this is what you have. It's a tube. Have a little weight in there. I have a marker here. Okay, a pen or marker, whatever. This is the unknown fluid here. Okay, that's what you have. I want you to measure the density. Okay, that's a goal. So now you have no clue how to design, right? Don't worry. Let the equation tells you. Okay. What is buoyancy force here? It's the gamma of the fluid times a volume, whatever volume is. I like it. See, immediately after I write this, my unknown, the thing I want to find, rho density of the fluid is in the equation, gamma F, right? Gamma is rho G, right? It's basically just density, okay? Then it's the weight of the object. Okay. Now, what you need to record in the experiment to find this is your goal. What you need to know. So you basically design some process to find out the volume and to find out the weight. Okay. So now you have a step, right? Just to find out these two. Probably you need a scale. Let's have a scale, okay? A scale, okay? A marker, okay? Then a tube. Is that right? And you can tell me? Now you can tell me what you plan to do. How do you do it? Unknown fluid with a scale, with a marker, with a tube. How to find out the weight? Well, that's too obvious, right?
Right.
Just use the scale, okay, to find out the weight of this object, okay? So volume, then the rest of the thing is volume. Okay, I need to put a subscript here. Volume submerged, right? It's not the entire volume of the object. I need the buoyancy force, right? It's the volume submerged. Okay, so how do I find out the volume submerged? Well, I just place this thing inside this unknown fluid. I use my marker here to mark the fluid line. Okay. Then I take the bottle out. You have a marker here. Okay, can you find the volume of this? Just pour some water into it to the volume line, this line. Maybe you can weight the water and divide it by the density, and it's a volume for water. We have a scale, right? Is that right? That's it, a marker. Well, usually hydrometer, you don't need a marker. They already have the automatic has the marker on the tube. You know, you put it in, they already can tell what is the volume. That's directly can tell you. But even without that, you can do it. See, this is the design process, right? I just want to convey this idea. It's not just fluid mechanics, okay? As an engineer, eventually you find out the best way to do the design is based on the equation. Based on equation, what do you have, what you don't. Try to find out the thing you don't have, okay? To design something. Then you have a clue, you have a direction to go how to design, okay? Not just based on experience. Sure, based on experience, it will be helpful. But even without experience, you should be able to do some design too, okay? Greater, when you're getting older, you have more experience, right? So when you started, that's a good way to do, okay? I guess that's it for today. I think we covered everything for chapter 3. It's done, chapter 3, okay? Content-wise, it's just, that's it. Let's do a quick review here. We'll start with the point pressure, Pascal's law, right? Point pressure, then surface force, then the buoyancy, okay? So these are the 4 topics in chapter 3, hydrostatics, okay? So I'm done with assigning all the homework problem. I have 2 sets of homework problem for chapter 3, okay? So let's practice it with those problems. I'll give you a quiz on Monday. Let's say it's a 10-point quiz. Maybe 1 problem would be 2 problems. Okay, so it's like a heavy-weighted quiz. Okay, for chapter 3. I said the focus on let's have maybe 2 problems. One is on the surface force. One is maybe on the other topics, including buoyancy, including point pressure, including the Pascal's law. Okay.
Is it still just a plain surface?
No, it's, let's say let's spend time on next Tuesday, as most of the time, let's do quiz, maybe 2 problem quiz. Okay, 1 problem will be the surface force, that's for sure. Okay, it's a section that I want you to fully understand, I want to emphasize. So you will have a problem for the surface force. Then the second problem will be either buoyancy or pressure calculation, or maybe even Pascal's principle. Okay, so. Okay, I guess that's it for today. Any questions? I still have a couple of minutes if you have any questions. Is that good? My explanation is clear, right? I hope it's clear. Okay, so everybody attend the class. You should spend not much time after class. Just spend time to practice. Okay, I suppose you fully understand now. Okay.
Could you say what those 4 main points of chapter 3 were again?
Oh, okay. I think it started with calculating the point pressure. Remember, in the tubes, every location you have pressure. We use a hydrostatic principle to calculate the pressure, and we have an alternative equation if you have multiple fluids, right? Remember, these are the content points for the pressure calculation. Okay, Pascal's law is kind of easy. It's just we have 1 example. There's a couple homework problems in there. Okay, then is the plane surface. Okay, let's say, hey, I don't need you to do the curved surface. How about that? There's a homework problem for the curved surface, but I won't test you. Okay, it's for you to understand using the alternative method like a horizontal or vertical virtual plane. Use that to find the force on the curved surface, just like I explained today. Okay, but let's focus on the buoyancy. So that becomes 4 topics in chapter 3.
Gotcha. Thank you.
Okay, you're welcome. You're welcome. That's the only place for hydrostatics, chapter 3 in the textbook. Okay, so hopefully everybody's good. Then we move on to the hydrodynamics. Okay, next week. Okay. Okay, so have a good rest of the day. Oh, any other questions?
No, thank you.
Okay, you're welcome. Have a good rest of the days and have a good weekend.
You too.
See you next week.